Module 9, Acid-Base Chemistry, the reactions between acids and covalent bases. Well, hopefully you have a good understanding about what happens when acids and bases that contain a hydroxide ion react. But what if that base doesn't have a hydroxide ion? What then? What if the base is a covalent molecule? You'll be happy to know that predicting the products of these reactions is easier than with a hydroxide base. Say we have sulfuric acid and mix it with water. Water is an amphiprotic substance. That means it can act as either an acid or a base. Well, when it is in the presence of an acid such as sulfuric acid, it will behave as a base. But water doesn't have a hydroxide ion. It isn't an ionic compound, but is a covalent compound sharing its electrons within bonds. Well, to predict the products of this reaction, you just need to remember the definition of an acid and a base, and you're good to go. Acids donate hydrogen plus ions, and bases accept them. So for a covalent compound to accept a hydrogen plus ion, we need to first look at what is going on with its Lewis structure. Here is a Lewis structure for a common covalent base, ammonia, or NH3. Notice that there's an unshared pair of electrons in this molecule. Hydrogen plus ions will want to go there in order to share the electron pair with the ammonia. And this is what goes on for all covalent bases. That means we can make a general statement for the products of acid-base reactions with covalent bases. Covalent bases accept only one hydrogen plus ion. Diprotic and triprotic acids require more than one covalent base to accept their hydrogen plus ions. This rule does have some exceptions, as you've seen for most chemistry rules, but we will not be learning about them in this course. So back to our example of sulfuric acid and water. Sulfuric acid wants to donate hydrogen plus ions. Because water acts as a base, it will accept a hydrogen plus ion and share one of its free electron pairs. That results in an H3O plus ion. But sulfuric acid wants to donate two hydrogen plus ions. That means we need to have two H3O ions in the products. The H2SO4 becomes an SO4 2- ion in the products too. So this is our final equation. Can you see the difference between when the base has a hydroxide ion? When it does, the products are a salt and water. When there's a covalent base, the products will be two ions. Let's look at another example. What reaction occurs between phosphoric acid, H3PO4, and ammonia, NH3, which is a base? Our acid is a triprotic acid, so it will donate 3 hydrogen plus ions. The base can only take on one, so we will need to have 3 ammonia molecules, which will make 3 NH4 plus ions. The leftover ion from the acid is PO4, and it will have a 3- charge because it lost 3 positive hydrogen ions. That's fairly simple to figure out, right? Now look at this one. What reaction occurs between H2Cr2O7, or dichromic acid, and water? You know the two reactants. H2Cr2O7 has hydrogens at the beginning, so it acts as our acid, and the water acts as our base. The acid is diprotic, but water can only take on one hydrogen plus ion. That means we will need 2 water molecules and will produce 2 hydronium ions. The leftover ion from the acid is Cr2O7, and it has a 2- charge from having lost the 2 hydrogen plus ions. And we're done. You now know the rules to predict the products of any acid-base reaction, whether the base is a hydroxide base or a covalent one. And you also know how to predict the products of a formation reaction, a decomposition reaction, and a combustion reaction. That's pretty amazing for just over a semester of chemistry education.